As you can see, this is the 2019 AP Calc AB free response numbers 1, 2, and 3. If you're sitting for the BC exam, the questions 1 and 3 were also on the 2019 BC test. So you would watch this video for the solutions to questions 1 and 3 from the 2019 BC exam. So let's go ahead and get started. Question number 1 says, we have fish entering a lake at a rate. So question number 1, we have fish entering a lake, so they're entering, so we call that E of T. Entering the lake at a rate of 20 plus 15 times the sine of pi t over 6. And we have fish leaving the lake at a rate of LT equals, and here we have 4 plus 2, and 2 is raised to the power of 0.1 t squared. They say that both ET and LT are measured in fish per hour, and T is measured in hours since midnight. So T equals 0 corresponds to midnight. All right, T equals 0 corresponds to midnight. Part A says, how many fish enter the lake over the 5-hour period from T equals 0 to 5 a.m.? Give your answer in the nearest whole number. So we want to know how many fish enter the lake. Remember, these are rates, right? These are rates. Rates mean that's the rate of fish per hour. That's not the number of fish entering the lake. That's the rate per hour that the fish enter the lake. And we know rates are derivatives. And since rates are derivatives, if we want to change a rate into an amount, we need the net change theorem, the fundamental theorem of calculus part 2, that says if we integrate a derivative, we undo the derivative. So if we want to know how many fish, for part A, how many fish entered the lake in the first 5 hours, that would be the integral of the rate at which the fish entered the lake between hours 0 and 5. And if we do that on our calculator, it's a calculator-based question, we get 153.457. Now it says in the directions to provide this answer to the nearest whole fish. So we would say the nearest whole fish, we would round down, so we have 153 fish entering the lake. Between midnight and 5 a.m. Okay. Now, question B, part B says, what's the average number of fish that leave the lake? So here we're going to have to find our average value of a function. We want the average number of fish that leave the lake. Remember, this is the rate at which they're leaving the lake. If we integrate this between 0 and 5, that would be 4 plus 2 to the 0.1 t squared dt, right? If we integrate that, that's going to tell us the number of fish that left the lake. We want the average number of fish per hour. It's over 5 hours, so we're going to multiply this by 1 over 5 minus 0, right, for our average value of a function. And again, it's a calculator-based problem, so we would just put that into our calculator. We would have already used the define function and put this into the calculator, and we get 6.059. And once again, they asked us, not this time for the nearest whole number, just the average. And so our average here is 6.059 fish leave the lake between 0 and 5 a.m. Part C says, at what time t between 0 and 8, so sometime between midnight and 8 a.m., is the greatest number of fish in the lake? When is the time that we have the most fish in the lake? So we have fish coming in, we have fish going out. We want to know when we have the maximum number of fish in the lake, right? Well, we know how to find the maximum number of a function. To find the maximum number, we take the derivative and set it equal to 0. These are already the derivatives. So we don't have to take a derivative. We don't have to physically take the derivative. We have the derivative, right? We have the derivative. So our answer to part C is, when is the rate of change, right? The rate of change going to be the greatest. And so what time is that going to happen? Well, that's going to be the fish entering the lake minus the fish leaving the lake, right? And we want to find the critical number for that. So we're going to set that equal to 0. Again, it's a calculator-based question, so we're going to ask our calculator to solve this. Now, we want it to equal 0 on 0 is less than or equal to t less than or equal to 8. So once again, knowing how to solve an equation on a defined interval is an important task. Otherwise, with this sine function, it's going to take your calculator quite a while to solve this. Now, if we do that, right, if we do that, we get t equals 6.20356. Okay. So a little after 6 a.m., right, a little after 6 a.m. is when we have our critical number. Now, we need to know, is that critical number a minimum or a maximum, right? When is the minimum? So what are we going to do? We're going to run the sine test here. Now, we start at 0, we end at 8, and our critical value is 6.20356. Now, this is our function, right? This is our derivative. Remember, that's our derivative. So we have ET minus LT, and we have those numbers stored in our calculator. We've stored our function already in our calculator. We need a number smaller than this, right? A number smaller. You pick any number you want smaller, like 6, 5, 4, 3, 2, something like that. And what we do, if we plug that in, right? If you plug in a test point here, you're going to find out that this turns out to be positive. All right, positive. And if you plug in a test point on the other side, over here, you're going to find out that the derivative turns out to be negative. Now, we know what that means. We means this is a local max, right? This is a local max. So, the greatest number of fish in the lake. Right now, the number of fish in the lake is increasing. Entering minus leaving is increasing. After 6 a.m., it's decreasing. So we have more fish leaving than we have entering. So we have the greatest number of fish in the lake at this time right here. This is when our population of fish in the lake is going to be the greatest. Okay? So we can solve this just by using our sine test and treating it like it's the maximum value on a graph. As long as we remember that the number of fish in the lake is the rate at which they enter minus the rate at which they leave, and those are already derivatives, right? Those are already derivatives. Now, part D says, is the rate of change in the number of fish in the lake increasing or decreasing at 5 a.m.? All right, now we're going to have to play some word games here. We want the rate of change right? The rate of change in the number of fish in the lake increasing or decreasing at 5 a.m. Right? That's what they asked us to find. for part D. Now, we want the rate of change in the number of fish, right? The rate of change in the number of fish. Well, this gives us the number of fish, and this gives us the number of fish, so we want the rate of change of those, right? We need to know the rate of change of those. Meaning, we need to find not E of t minus L of t, we need to find E prime minus L prime. We're working on the second derivative here. We're working on the concavity. But of course, the first derivative doesn't have a prime, so the second derivative only has one prime. Now, we need to know, right, what's the rate of change in the number of fish in the lake? Is it increasing or decreasing at 5 a.m.? Well, that means we need to find E prime of 5, right, 5 a.m., minus L prime of 5, the rate at which the rate is changing. That's what they want to know. It's two rates. And so what do we get? We would plug these into our calculator. We would take the derivative of this minus the derivative of this. We would define those functions, plug in a 5, and if you do that and do the arithmetic correctly, get negative 10.7228. Now that's less than 0, right? That's negative. So, because it's less than 0, the number of fish in the lake is decreasing at I'm sorry. That is wrong. The rate at which the number of fish in the lake is changing at t equals 5 is decreasing, right? The rate at which the number of fish in the lake is decreasing. So, if we put that together, right, if we put that together with what we know down here, let's see how this goes together. This says the number of fish in the lake is increasing. 5 a.m.'s right here, right? Here's 5 a.m. This says the number of fish in the lake is going up. It's going up. But its rate of change is going down, right? So it's been going up, but now it's going up slower. So at 5 a.m., right, at 5 a.m., here's the graph down here, here's 5 a.m., our rate of change at 5 a.m. is less than our rate of change was over here. It's decreasing, right? It's going up, but the rate of change is getting smaller. So the number of fish coming into the lake is increasing, but it's increasing slower than it was maybe at 3 a.m. or 2 a.m. or something like that. All right? That's question number 1. Now, that, like I said, that was also a BC question. So now we'll move on to question number 2. Question number 2 was an AB question only. So I'll tell you what I'm going to do. I'm going to go ahead and do question number 3 right now. That way the BC kids can watch question 1 and question 3 and then exit out of this video and go off to the BC video. And those of us looking at the AB video will stick around for question 2 at the end. Okay, so we're going to do question number 3 right now. So we'll skip ahead to question number 3 because again, this is on the BC test and this is on the BC test. Both of them are on the BC test. We'll just do those in order. So let's see what question number 3 asked us. Question 3, they give us a graph of a continuous function on the closed interval from, well, we know it's continuous, right, from -6 to 5. -6 to 5. And it says, the figure above shows a portion of the graph of f consisting of 2 line segments and a quarter of a circle at the point 5,3. Centered at the point 5,3, I apologize. It is known that the point 3, 3 minus root 5 is on the graph. Okay, so we're going to draw this over here because we're going to need it throughout the problem. Now, what have they told us? They told us our function is continuous and defined on, so f is continuous on and they told us it was continuous from -6 to 5. But they didn't show us the whole graph. The graph goes from -1, 1, right, -1, 1 here, up to -2, 1 right here. And so this line has a slope of -1. And then from there, it goes up to 2, 3. Goes to 2, 3. Okay. And from there, we get a quarter of a circle going from 2, 3 down to 5, 0. So we get a quarter of a circle right here. Right? What do we know about our circle? We know that the point 3 minus root 5. Oh, I'm sorry, I drew this graph wrong. Let me erase this. Apologize for the interruption here. This goes to 2, 3. And then we have a quarter of a circle going down to 5, 0. And we know this point right here at 3, we know this is the point 3, 3 minus root 5. Okay, that's what we know. And the center of our circle is at 5, 3. So the center of the circle is right here. We'll label that center. So we know the radius of our circle, right? We know the radius, that's 5, 3, that's 5, 0. So we know the radius equals 3 for our circle. All right, so there's our picture. This is our function f. Part A says, if, right, if the integral from -6 to 5 of f of x dx equals 7, find the value, the integral from -6 to -2. -6 to -2 of f of x dx. So we don't know what the rest of the graph over here looks like, right? It goes all the way to -6. So let's just say the graph goes like this, and this is our point -6. Okay? What do we know right now? Right now, if we shade in the area under the curve, we know that area is 7. Right? That area is 7. Because it says the integral from -6 to 5, -6 to 5, the area under the curve is going to equal 7. They want to know what's the area from -6 to 2. Okay. Well, we can find this area right here. This is 1 wide by 1 high. The area of this is a half. This is 1 wide by 1 high. The area of this is minus 1 half. Now this, right, we have a triangle over here, right? We have a triangle here. So what do we know about the red triangle? Well, it's 2 wide by 3 high, so the area of that's 2, right? What about this triangle down here? Right? What about this triangle down here? Now we're going to have to figure that out. What's the slope of this line? Well, it goes up 4. It goes from -1 to 3. That's up 4. It goes over 2. So the slope of this line is 1/2, right? 1/2, which means this point is 1/2. So this is 1/2 wide by 1, but it's a triangle, so the area under here is -1/4. Now, what do we have over here? What do we have for this piece right here? Well, that's a circle, but it's a fourth of a circle, right? So its area there is going to be the area of that circle, which has a radius of 3. So the area of the whole circle is going to be 3 squared, 9 pi, but we only have a fourth of it, so we get 9 pi over 4. So what do we know right now? We know this area, pardon me, we know this area, the area from -2 to 5, is going to be 1/2 minus 1/2, right? So I'll just write it all down. It's 1/2, then it's minus 1/2, then it's minus 1/4, then it's plus 2, and then it's plus 9 pi over 4. So what do we get? We get 9 pi over 4, half and half minus, they cancel, pardon me, half and minus half cancel. I get 2, which is 8/4, minus 1/4, so I get plus 7/4. So that's the red area, right? That's all of those added up, 7/4 plus 9 pi over 4. Now, what is the area here going to be? Well, we know what this area is going to be. It's going to be the area of the entire thing minus the area we have. Because we have a theorem that says the integral from -6 to 5 of f of x dx is equal to the integral from -6 to -2 of f of x dx, that's the part we need, plus the integral from -6 to, sorry, that's wrong, from the integral from -2 to 5 of f of x dx. Well, what do we know? We know the entire thing is 7, right? This is the part we're trying to find. We know this piece is 7/4 plus 9 pi over 4. So the part we need, right, the part we need is 7 minus 7/4 plus 9 pi over 4. And what is that going to equal? Well, 7 is 28/4, right? Minus 7 gets us 21/4 minus 9 pi over 4. All right? So we're working on number 3. So I added something wrong somewhere, I guess? Why didn't you guys tell me I was adding something wrong? Because they got 11. Right? They got 11 here. Where I got 9 pi over 4 plus 7/4. They got 9 pi over 4. Well, I'm going to have to figure this out. Give me just a second here to think about this. Obviously, I can't. Well, there's the magic of editing. That drawing was so wrong in so many places I couldn't even fix it. So I'm just going to start over. So I apologize for those of you that had to sit through the beginning of that problem. But here we go, number 3. Let's see if we can do it right this time. Let's see if we can draw the picture correctly. All right, so we need the graph, and we need to draw the graph correctly. So for those of you that patiently sat through that last problem, I'm about to start it again, right? So all right, here's -1, here's -2, and our first line segment goes like this, right? So this is -2, 1. This is 0, -1. Here's 1, here's 2, here's 3, here's 4, here's 5. Then we go up to, right? We go up to 2, 3. All right. Now the slope of this line is +2, not 1/2, and therein lies our problem, right? Now, from 2, 3, we have a quarter of a circle that comes down to 5, 0. Done. All right. now let's see if we can do part A, right? Let's see if we can label these areas correctly first. So, I think we can all agree that the area right here is 1/2. I think we can all agree that the area right here is negative 1/2. From here, everything I wrote before this was wrong. All right, what do we got over here? We have a box. And the area of the whole box is 9, right? It's 3 by the bottom. It's 3 by the top, because remember, this is the center of our circle, and that's 0.53. So the area of that box is 9. Minus the area of this piece, because we want this area right here, don't we? So it's going to be the whole box minus the quarter of the circle. The quarter of the circle is 9 pi over 4. So with the whole box, 9 minus the quarter of the circle. Now let's see if we can get these right. That slope is 2, which means, although it's not drawn very well, this point right here is 1/2, right? 1/2. So it's 1 high, 1/2 wide. 1 high, 1/2 wide. So that has an area of 1/4, but it's below the x-axis, so that's going to be negative 1/4. Now this triangle has a height of 3, a base of 3 halves, right? So the area of that triangle has a height of 3, it has a base of 3 halves, and it has a half, because it's a triangle, we get 9/4 there. All right, now we're ready to go. Now we have all of that labeled. And what did they tell us? They told us this problem, this function continues on out here to -6, right? -6. And so in part A, they told us the integral from -6 to +5 of our function f of x dx was 7. They asked us to find the integral from -6 to -2 of f of x dx. Well, we can use our property, well, let's not write it down, we'll just write it in terms of the problem. The integral from -6 to 5 of f of x dx is going to equal the integral from -6 to -2 of f of x dx plus the integral from -2 to 5 of f of x dx. And what do we know? We know this is 7, right? We don't know what this is. We'll just put a question mark for that. That's what they asked us to find. Plus this piece over here. And we can write that piece down. It's a half minus a half, because that's below, minus a fourth, right, because that's below, plus 9/4, because that triangle's above, plus 9 minus 9 pi over 4. So what do we get? A half cancels a half. This into here, right? That makes 8/4, so that's 2. 2 plus 9 is 11, so we have 7 is equal to the part we want, plus 11 minus 9 pi over 4. So if we move these over here, we get that the integral from -6 to -2 of f of x dx equals, we bring that over, that's a -4, we bring that over, that's positive, so we'll write that first, 9 pi over 4 minus 4. Wow, what was that? All right, let's do part B. Part B says to find, right, find the integral from 3 to 5, right, 3 to 5, now 3 is here, right, the integral from 3 to 5 of 2 times f prime of x plus 4 dx. Now we know if we integrate a derivative, we get this, right? The integral makes the derivative go away. Plus 4, the integral of 4 is 4x, and we're evaluating that between 3 and 5. So what is that going to equal? Well, that's going to be 2, right, times f of 5 plus 4 times 5, plugging in my upper bound, by the fundamental theorem of calculus, minus 2 times f of 3 plus 4 times 3. Now we know f of 5. They told us f of 5 was 0, right? F of 5 is 0. So this is 2 times 0. So this is 20, right? 0 plus 20. Over here, f of 3. Now they told us f of 3, right? They told us f of 3 was equal to 3 minus 3 root. So it's 3, comma, 3 minus root 5. So f of 3, right, minus, we got 2 times that. So that's going to be 6, right? 2 times this, minus 2 root 5, plus 4 times 3 is 12, isn't it? So what do we get when we're all done? We get 20, right? And so we have 2 times f of 3, right? F of 3 was this, so we have 6. I'm sorry, that's a minus, isn't it? So we have 20, we have a minus 6, we have plus 2 root 5, and we have a minus 12. So what do we get? We get 20, take away 18, that's 2, right? Plus 2 root 5. Let's see if we actually got that one right. Hey, look at that. We got one right. Huh. Now for part C. All right, let's see what part C gives us. Part C gives us a function g. All right, so let's clear off some space over here. So part C says we're given the function g of x, which is equal to the integral from -2 to x of f of t dt. So it looks like it's going to be the fundamental theorem of calculus. Find the absolute maximum value of g on the interval -2 to 5. Now we know to find an absolute max, we're going to have to test the endpoints and any critical values, right? That's what we're going to have to do. We're going to have to test the endpoints and any critical values. So we have to ask ourselves, right? We have to ask ourselves, is there anywhere, right? Is there anywhere g prime equals 0 or fails to exist? Now what is g prime? G prime of x is the derivative of this, so that's just f of x. So is there anywhere between -2 and 5 where f of x, which is g prime, equals 0? Well, yeah, it equals 0 right here, and it equals 0 right here, right? Those are going to be two critical values for us. So our critical numbers are x equals -1 and x equals 1/2, and our endpoints are x equals -2 and x equals 5. So what do we need? We need a table. We need x and we need g of x, right? Because we got to find the absolute maximum. So we have -2, right? -2. We have -1. We have 1/2, and we have 5. So what is g of x? G of x is the integral from -2 to -2. Well, it's going to be 0. What is g of -1? G of -1 is the integral from -2 to -1. The integral from -2 to -1 is 1/2. What is g of 1/2? That's the integral from -2 to 1/2. So that's the integral from -2 to over here at 1/2. We get 1/2, take away a fourth. That's going to be minus 1/4. And then we need g of 5, right? G of 5. We just found g of 5. Well, we used it in the previous problem, right? It was 11 minus 9 pi over 4. Now, it says find the absolute maximum value, right? Well, clearly the negative is smaller than 0. 0 is smaller than the half. And a half is smaller than 11 minus 9 pi over 4. So our absolute maximum value is g of 5, right? G of 5. This is our absolute max. All right, what about part D? Part D says find the limit. All right, we'll work that right here. They want us to find the limit as x goes to 1 of 10 to the x minus 3 f prime of x divided by f of x minus arctan of x. All right, let's plug in 1 and see what we get. Probably going to get 0 divided by 0. Let's see what happens. We put a 1 in here, we get 10, right? Now, as x goes to 1, this is f prime of 1, right? F prime of 1. F prime of 1 is right here. Here's 1. F prime of 1 is 2, right? So our numerator is going to be 10 to the first minus 2, so I was wrong, it doesn't turn out to be 0 divided by 0. What's f of x? Well, that's f of 1, right? F of 1 is 0 minus inverse tangent of 1, right? When does tangent equal 1? Tangent equals 1 at pi over 4. So what do we end up with when we're all done here? We end up with 8 divided by negative pi over 4. All right, 8 divided by negative pi over 4. Oh, I forgot to multiply by the 3. By the 3. This is 3 times 2. This is 6. Hey, I caught that one. So this is 4. There we go. 4 divided by negative pi over 4. So what does that equal? That equals negative 16 over pi. I don't know. Let's see if we got that one right. Yeah, I think we did. Okay. Man, I'm having a bad day. F of 1 is not 0, is it? No. That line has a slope of 2. So f of 1 is 1. So this is 1. Well, it doesn't clean up nearly as nice as I thought it did. So our answer is just 4 divided by 1 minus pi over 4. All right. Hey, that's the end of question number 3. So the BC kids can finally leave this disaster of a video and go back and pick up theirs. And you AB kids, you got to stick around for me to mess up question number 2. See if I can get that one wrong as well. All right. All right, so here we go, AB kids. Let's see what's going on in question number 2. Let's see if I can get one right without screwing it all up, huh? See what we can do here for you. Running out of whiteboard cleaner. All right, let's take a look at question number 2. Question number 2 is velocity problem. It says the velocity of a particle p moving along the x-axis is given by the differentiable function v of p, where Vp of t is measured in meters per hour and t is measured in hours. Selected values of V of P of t are shown in the table above. Particle p is at the origin at time 0. All right. Now let's make sure we understand this. The velocity is differentiable, right? V of p is differentiable. Since it's differentiable, V of p is continuous, right? It's continuous. So part A, now they didn't tell us the function, they just gave us numerical values. They gave us a table. Part A says justify why there must be at least one time t between 0.3 and 2.8 at which v prime, the acceleration of the particle, equals 0 meters per hour. All right? So let's take a look at this. This is number 3. Number 3. And what do we know about our particle? What do we know about our particle? Well, if we look at our table, right, they gave us this interval in part A. And the interval they asked us to talk about is 0.3 to 2.8. Why must the derivative of v prime equals 0 at least once, right? Why must that happen between those points? Well, does this sound like anything we've worked on before, right? It does, doesn't it? It sounds like the mean value theorem. That's what it sounds like. Because we know, right? What do we know? What did they tell us? They told us v sub p is differentiable, which means v sub p is continuous, right? It's continuous. So what does that mean? Well, we know the mean value theorem has to apply. So what is the slope of our secant line? What is the slope of our secant line between time 0.3 and time 2.8? Because what did we say about the mean value theorem? We said about the mean value theorem, remember, if you have a function that goes like this, what we said is if you look at the slope of the secant line, and if your function is continuous, somewhere on that interval, the slope of your tangent line has to equal the slope of your secant line. Those things have to be true. That's what the mean value theorem said, right? The mean value theorem said the integral, well, mean value theorem, it said f of b minus f of a over b minus a has to equal f prime of c for some c in A to B. Right? It's got to be true. The derivative has to equal the slope of the secant line. So what's the slope of our secant line? Well, if we go look at our table, right, and we look at the numbers they asked us to find, what's the slope of the secant line? Well, the slope of the secant line at 0.3, right, at 0.3 we have our y value of 55. And at 2.8, you know, funny thing, we have another y value of 55. So the slope of the secant line is 0. Therefore, we know at least once by the mean value theorem, the slope of the tangent line has to equal the slope of the secant line. The slope of the tangent line is the derivative, so therefore the derivative has to equal 0 by the mean value theorem. All right, so that's part A. Part B. Use the trapezoid sum with the 3 subintervals. Okay, so I'm going to erase this little mean value theorem drawing we did here. We're going to go ahead and put down our x-axis. And we start at 0, and at 0 we're 0 high, right? And we go all the way to 4. So we have, call this 2, call this 3, call this 1, here's 4. At 4, we're 48 high. Okay, so we'll just call this 48. At 2.8, we're 55. So now remember, that's 2.8. We're at 55, so we're taller than that, right? 55. At 1.7, we're negative 29. And that was 1, that was 2, that was 3, right? That was 4. Now, our given values, remember, are 2.8 and 1.7, right? And at 1.7, how tall are we? We are negative 29. Our velocity is negative 29. So we're down here, right? And at time 0.3, right, 0.3, right here, 0.3, we are 55 high. So we're back up here, 55. Okay. Now they want us to use the trapezoid rule, right? The trapezoid rules. What is that? With intervals from 0 to 0.3, 0.3 to 1.7, and 1.7 to 2.8 to approximate the value. So they want us to approximate the integral from 0 to 2.8 of Vp of t dt using the trapezoid rule. So first we're going to have to draw all of our trapezoids, okay? We're going to have to draw our trapezoids. So let's see what we can do with that, right? Now, what do our trapezoids, we go from 0 to 0.3, right? 0 to 0.3. So, that's going to look like this. And then we go from 0.3 to 1.7. And then we go from 1.7 to 2.8. Okay? Now they want us to use the trapezoid rule. All right. So we have to remember the trapezoid rule, right? That's what we have to do now. So what do we remember about the trapezoid rule? Well, the trapezoid rule, we take the average of the two endpoints times the width, right? So here we would have v of 0 plus v of 0.3 divided by 2, right? That's our height, trapezoid, times the width. The width here would be 0.3. Okay. Plus, now how far is it from 0.3 to 1.7? It's 1.4. So our height here would be v of 0.3 plus v of 1.7 over 2 times the width, which is 1.4, plus, there's some room here so we use it. Here we would have v of 1.7 plus v of 2.8, all divided by 2, times the width, 1.7, that's 1.1. Okay. Now, if we do all of that math correctly, and I'm not going to work out the arithmetic here, we should get 40.75. Right? So remember, the trapezoid rule is the average value of the heights, so you add them together and divide by 2, times the width. All right? What about part C? Let's see what part C says. A second particle, Q, moves along the x-axis so that its velocity between 0 and 4 seconds is given by. All right, so now we have a second particle Q. So let's talk about our second particle Q. All right, this is our particle P. So we have particle Q. So this is part C. So the velocity of particle Q is given by, now we don't have a table here, we have a function. It's 45 root t cosine. 45 root t times the cosine, thank goodness this is a calculator problem, the 0.063 t squared. Okay. Meters per hour. Find the time interval during which the velocity of particle Q is at least 60 meters per hour, and find the distance traveled by particle Q during the interval when the velocity is at least 60 miles per hour. So we want to know, when is the velocity of this particle between 0 and 4, right? Between 0 and 4, when is the velocity of this particle 60 miles per hour? So, how are we going to solve that? We're going to solve on our calculator v sub q of t, that equation right there, equals 60. We're going to ask our calculator for that solution. Now, when we ask our calculator for that solution, once again, we want to ask it to solve between 0 and 4, right? You need to learn that skill. Otherwise, you're going to sit there for 12 minutes waiting for your calculator to come up with a billion answers. And the times we get, again, I'm not going to sit here and plug this into a calculator for you. The times we get two of them. The times are 1.866, 181. That's time A. And then time B, we get 3.519, 19174. Okay? Those are when it equals 60. Now we need to know when it's greater than 60. So what are we going to do? This is when it equals 60, right? So remember, we're starting at 0, we're going to 4. Well, we know right here, this is time A, and right here, this is time B. We equal 60 at both of those, right? So this is 60, and this is 60. Well, what are you going to do? You're going to pick a number smaller than this and plug it in. Right? Pick a number smaller. Plug it into here with your calculator. You've got a defined function. And you're going to find out here you're less than 60. So if you plug in a number smaller than this, like 1, if you plug 1 in here, you're going to get a number less than 60. Okay? If you pick a number between here and here, this is 3.5, right? 3.5, so pick 3.9. You plug that in, you're going to find out this is less than 60. And then pick a number between the two, like 2. And you're going to find out this is greater than 60. So this, by just plugging in numbers, this is where we're greater than 60. Okay? And that's what the question asked. The question asked us, when is, find the time interval during which the velocity of particle Q is at least 60 miles per hour. Okay, we did that. Now it wants us to find the distance we traveled, right? The distance we traveled. Well, now this is where we have to remember. Distance, right? We're gonna get distance here, not displacement. So that's going to be the integral from time A to time B, absolute value of V of Q. Now we're going to do that on our calculator. We're going to put in the absolute value. We have to know how to turn on the absolute value key. It's under the catalog button. If you don't know how to do that, you need to look that up on a video. All right? So the answer there is going to be this integral. And I'm not going to plug that in for you, but it gives us an answer of 106.010874 meters. 106.108.754 meters. So here we have to remember that if we want the distance traveled, we have to be able to take the integral of the absolute value of velocity. If we just took the integral of velocity, it would give us displacement, right? Displacement. All right. So that's part C. I'll clean this off here and see if we can do part D. Okay. All right, part D says, let me read it here real quick. At time t equals 0, particle Q is at a position x equals negative 90. Okay. Using the result from part B and the function v sub q from part C, right, which I just erased, but we have it written right here on the paper, approximate the distances between particles P and Q at time t equals 2.8. Okay. So how far apart are the particles at time 2.8? Where are they and how far apart are they, right? How far apart are they? Well, we did that right here, right? We found the integral from 0 to 2.8 for particle P. So this is the position of particle P, right? This is the position of particle P. Now, I say it's the position of particle P because particle B started at 0, 0. It started at x equals 0. That's where it started. They told us that. They told us it started at x equals 0. So its displacement, right, its displacement is 40.75. 40.75. That's its displacement. So it started at 0, and the displacement from where it started to where it ended up was 40.75. Now I don't know its distance. We didn't calculate that. We calculated displacement. So this is where it is at t equals 2.8. This is a story of particle P, right? Now, what about particle Q? Right? Where is particle Q? Well, we're going to have to think about particle Q carefully. They gave us a formula for the velocity of particle Q. Right? They gave us a formula. What did they tell us? They told us, let's go ahead and write that down. They told us the velocity of particle Q was 45 square root t cosine 0. I'm doing this out of memory. 0.063 t squared. Let me look that up. Make sure that's right. Yes. Okay, that's right. And they tell us at time 0, right? Now this is time. Let's go back to green. This is t equals 0 for particle P. This is where we are. We're at 0. So what does the graph of particle Q look like? Well, at t equals 0, we're down here at negative 90. Right? That's our position. Negative 90. Right? That's what it says. At time 0, the position of particle Q is negative 90. Okay. So now we have to know where is particle Q, right? Where is particle Q at time 2.8, right? Well, what are we going to do? We're going to find its displacement. We're going to find out how far it moved, right? That's what we're going to do. And if we find out how far it moved from here, that will tell us, okay, I started here, I moved 100. Okay, if you moved a positive 100, not distance, if your displacement is positive 100, then you're sitting right here at positive 100. That's where you are right now. All right, that's your displacement is 100 from here. So you went 100 from here, so you're at 10. So how are we going to do this? Well, we have this. We're going to look at this. Let's look at the integral from 0 to 2.8, right? 0 to 2.8 of v of q of t dt. Now, we can find that on our calculator, right? We can find that on our calculator. And if we do find that on our calculator, you get 135.937653. Now, we also know what that equals. That's equal to, right? That's equal to the position, right? This is velocity. So if I integrate velocity, I get position. This is equal to the position at time 2.8 minus the position at time 0, because the integral of velocity is position. Now, they told us, right? They told us that this position right here is negative 90, right? Negative 90. So we have the position at particle 2.8 minus negative 90. So that's the position at time 2.8 plus 90 equals this. So we bring the 90 to the other side, right? And what do we get? When we bring the 90 to the other side and subtract, we're going to get the position at time 2.8 is equal to this minus 90, so that's going to be 45.937653. So we used the fundamental theorem of calculus here. We took the derivative of the velocity, we got position, right? We've done that many times. We move the 90, two negatives make a positive. We move the 90 over here and we get this. So where is particle Q, right? Where is particle Q at time t equals 2.8? Well, it's sitting at 45.937653. Now they asked us how far apart are the particles? So we have to subtract. How far apart are the particles? Okay? That takes care of question 3. All right, so that's it for this video. I'll post the next video with questions 4, 5, and 6.